Savvy clients I see, but for those who aren't, you could learn all about the Savvy program at the website www.savvymx.com. Enough for preliminaries. Our subject tonight is EGT and CHT, and as you can see, there's a lot to discuss in the next 45 minutes. So let's plunge right in. There we go. Okay, I'd like to start out with a little history of EGT and EGT instrumentation. As I said, I've been flying and an aircraft owner for quite a few decades, and I remember in the late 60s when I installed an exciting new instrument in my Cessna 182 from a company called Alcor, and it was an exhaust gas temperature gauge, and we'd never had any EGT instrumentation until the late 60s. And it was introduced originally by a company called Alcor that was owned by a petroleum engineer by the name of Al Hundari. The original EGT indicators were very, very simple. They were a little steam gauge like the one on the left there. They were connected to a single thermocouple probe that was located in the exhaust cluster somewhere, and that was the original EGT instrumentation. The interesting thing about those gauges, it wasn't particularly interesting at the time, but it's interesting in a historical perspective, is that if you look at the original EGT gauges, like this Alcor one right here, you'll notice that there are no numbers on the instrument. The instrument has a scale, and the scale is calibrated with little tick marks, and those tick marks are worth 25 degrees Fahrenheit per division. There's a little yellow reference pointer that can be adjusted with this little knob. Some of the instruments had that. Some of them had a fixed reference pointer, this little asterisk. But basically there are no numbers on this instrument. What this instrument does is it lets you see relative EGT, but not absolute EGT. Now, what do I mean by that? Relative EGT is the EGT relative to peak EGT. So the way you use these instruments is you would you'd lean the engine until EGT peaked. You'd set your reference pointer at that peak, and then you would enrich, and typically in those days we only operated rich at peak. You would enrich until EGT dropped a certain amount from peak. So we would typically operate at 100 or 125 degrees rich at peak EGT, but nobody had any idea what the EGT actually was in absolute terms. It was all we had was relative information. We knew what our EGT was in relationship to peak, but we didn't know what the absolute value was. Later on, in the early 70s, we started to see the first things that were called engine monitors. They were very primitive. The Alcor unit in this middle picture is an example of that. And it was basically 4 or 6 of these analog EGT gauges all stacked up into a single instrument package. And again, these instruments displayed only relative EGT values, not absolute EGT values. And then later on in the 70s, Insight introduced the graphic engine monitor, the GEM, which was the very first digital engine monitor. It similarly had a display with no EGT numbers on it. There was actually a CHT scale here on the right, but the EGT scale had no numbers on it. It was simply a relative scale. And once again, we used these instruments. We leaned to a peak value, and then we could enrich or lean to bring the EGT down a certain amount from peak. And very similar to the analog gauges, each little segment on these digital bar graphs was worth 25 degrees Fahrenheit. So although the display was more sophisticated and the software did some fancy things like lean find and all that stuff, we were looking at relative information only when it came to EGT. This turned out to be a good thing. Things got a little bit messier when a company called Electronics International introduced an instrument called the US-8, stands for Ultimate Scanner 8, and it was this instrument here. And for the first time, these guys presented EGT information, CHT and EGT information, not as relative values, but as absolute digital values. Here we're looking at 1323 degrees Fahrenheit or 1365 degrees Fahrenheit. And of course their marketing material was touting the fact that now for the first time you could see your EGT with 1 degree accuracy and know exactly what it was. This turned out to be a bad thing for a reason that we'll get into, but basically it started causing pilots to start obsessing about absolute EGT values and comparing their EGTs with the EGTs that their friend was getting in their airplane, and why is mine higher and yours lower, and all sorts of stuff like that. Then a little bit later, a new startup company called JP Instruments came out with what ultimately wound up being the best-selling engine monitor in history, called the EDM 700. That's this instrument here. And what JPI did was to combine the bar graph display that Insight had on its gem with the digital readout that Electronics International had on its scanners. And these things started selling like hotcakes, and of course subsequently the various competitors like Electronics International and Insight and ultimately other firms started coming out with instruments with the same kind of thing, where they had both a graphic display and an absolute digital display showing absolute temperatures. So the genie was out of the bottle. Pilots started fixating on these EGT numbers and using them in all sorts of inappropriate ways. And as I said, this turned out to be a major distraction and a bad thing. And the reason it was a bad thing is because these EGT absolute values are basically meaningless numbers. And the reason that they're meaningless is that EGT is not a real temperature. So let me show you what I mean when I say EGT is not a real temperature. Let's take a look at what an EGT instrument that displays absolute EGTs is actually displaying for you. Now this is a little bit complicated, so follow me through it, please. Here we have a complete set of 2 crankshaft rotations, 720 degrees, and we're watching what's happening in a particular cylinder. We start up here, and this upper graph, this blue wiggly line, is the piston position, and it starts at top dead center, and during the intake cycle or intake stroke, the piston goes down to bottom dead center. Then the piston comes back up to top dead center during the compression stroke. Then it goes back down to bottom dead center during the power stroke, comes back up to top dead center during the exhaust stroke, and then the whole process repeats. So this is simply the way the piston is moving during 720 degrees of crankshaft rotation. Now let's take a look at the temperatures inside the combustion chamber. If we were able to put a temperature probe inside the combustion chamber, here's what we would see. During the intake stroke, the exhaust valve closes it was open during the exhaust stroke, and early in the intake phase the valve closes, the intake valve is open, and the cylinder is breathing in nice cool fresh air with some fuel mixed into it. And of course the temperature in the combustion chamber is low, and it gets lower and lower as this cool fresh air gets ingested into the cylinder. Then the piston starts back up. Fairly shortly after it does that, the intake valve closes, and we start compressing this cool fuel-air mixture. As it gets compressed, it starts heating up. Then the spark plug fires, and this fuel-air mixture starts to combust. And at that point, the temperature starts rising very, very, very rapidly. It rises up through top dead center. It keeps rising until it reaches a peak, which is typically about 16 degrees or so after top dead center. This is the peak pressure and peak temperature point in the cycle. And then as the combustion continues and the piston starts moving down and the gas expands and is being converted into power, into crankshaft rotation, the combustion temperature starts declining quite rapidly. When the piston is almost at the bottom of the stroke, the exhaust valve opens, and then the piston starts heading up and starts ejecting this exhaust gas out the exhaust port. When the piston is almost at top dead center again, the intake valve opens in preparation for the intake stroke. And you'll notice there's actually a period of time from here to here where both valves are open. It's called the valve overlap period. It's a fairly short period of time when the intake valve has started opening and the exhaust valve hasn't closed yet. At any rate, that's what we would see if we were able to put a temperature probe inside the combustion chamber. But, of course, we don't have temperature probes inside the combustion chamber. We have EGT probes. EGT probes are mounted in the exhaust riser pipe, typically 2 to 4 inches from the exhaust valve. So during the entire period when the exhaust valve is closed, even though there's all sorts of wild stuff going on inside the combustion chamber, the EGT probe doesn't see any of it because the exhaust valve is closed and the EGT probe is outside of the exhaust valve. It's not in the combustion chamber, and it's basically seeing nothing particularly interesting during about 2/3 of the cycle, 2/3 of the time. Then, when the exhaust valve finally starts to open during the exhaust stroke, all of a sudden the EGT probe starts seeing some real interesting stuff. And what does it see? It sees exhaust gas which starts out very, very hot, not anywhere near as hot as the peak in the combustion chamber. That's up around 4,000 degrees Fahrenheit. But it sees a pulse of gas that starts off quite hot, somewhere close to 2,000 degrees. But then as the exhaust stroke continues and the pressure goes down and this gas is being allowed to escape from the combustion chamber, it cools down very, very rapidly. And then after the exhaust stroke is over, the exhaust valve closes, and now the TIT probe sits there for 2/3 of the time not seeing anything. So what the EGT probe is seeing is it's seeing short pulses of rapidly changing gas temperature, punctuated by long periods of nothing. And of course the probe, which has a fair amount of thermal mass to it, is trying to integrate all of this rapidly changing temperature stuff, and it settles at some indicated or some equilibrium temperature, which it dutifully reports to our EGT gauge. That temperature is not really a gas temperature, as you can see. It's the only thing you can say that it's a temperature of. It's the temperature of the probe. Wherever that probe finds equilibrium in the face of all of this rapidly changing temperature and rapidly changing flow, is what is reported on the EGT gauge. And so the EGT really has very little relationship to any of the combustion temperatures, because during the interesting part of the combustion process, the EGT probe is blind. It can't see anything. And that's why I say EGT is not a real temperature. And the absolute value of EGT, whether it's, 1250 degrees or 1410 degrees, is not a particularly meaningful number. It's not like the probe was sitting there in a smooth gas flow and it had a chance to settle in at the gas temperature. The gas temperature is constantly changing, and the probe just winds up at whatever temperature it happens to wind up, given all of this rapidly changing stuff. Okay, so now that we know what EGT isn't, and it really isn't related to combustion temperature, let's talk about what it is. In fact, let's talk about what EGT and CHT are. And what they are their measurements of how much energy the engine is wasting. Our engines, our piston aircraft engines, are remarkably inefficient at converting the latent energy in avgas into useful power. In fact, under the very best of circumstances, with everything just as optimum as it possibly can be, the very best that we ever get out of a piston aircraft engine is about 1/3 efficiency. In other words, only about 1/3 of the energy in the fuel, latent in the fuel, is actually converted into useful work, turning the crankshaft, turning the propeller, and propelling us through the sky. And at least 2/3, and often more than 2/3 of that energy is wasted. And it's wasted in a number of different ways. About half of the energy in the fuel simply goes out the exhaust pipe. The engine extracts as much energy as it can from the fuel, which is typically only about 1/3, and most of the rest of that energy winds up simply going out the exhaust pipe, roughly 50%. If we have a turbocharged engine, we recapture a little bit of that energy that would otherwise be wasted, because we make it drive a turbine and get something useful out of it. But basically, half the energy in the fuel simply goes out the exhaust pipe, which is a little depressing in an age of $5 and $6 avgas, but that's the way it is. The next largest chunk of energy is lost to heating up the cylinder. If the cylinders were perfectly efficient, they'd run cold, because all of the energy in the fuel would get converted into mechanical energy, and none of it would be converted into heat energy. But unfortunately, the cylinders are anything but efficient. They're very inefficient. And roughly 15% of the energy latent in the fuel winds up simply being dissipated as heat by the cylinder. And in our air-cooled engines, that heat winds up being transferred to cooling air. Another small portion of that energy winds up being wasted heating up the oil. And our aircraft engines deal with that heat by passing the oil through a little radiator called an oil cooler and dissipating that heat into the air as well. So basically 2/3 of the energy in our fuel winds up heating up the air and not propelling the airplane. And there are 3 major ways that energy is, that 2/3 of the energy is wasted. The biggest portion out the exhaust, a smaller portion from the cylinder fins, and an even smaller portion through the oil cooler. We have cockpit instruments that let us watch the amount of energy that's wasted. The instrument that lets us watch the energy wasted out the exhaust is called an EGT gauge. And that's what EGT means. EGT is telling you how much of the energy in the fuel is being thrown away out the exhaust pipe. We have a CHT gauge that gives us an indication of how much of that energy is being lost through heating up the cylinder, and we have an oil temperature gauge that shows how much of it is being wasted heating up the oil. And then we have one more gauge that actually indicates how much of it is being turned into useful work, and that's our airspeed indicator. It doesn't show us the power directly, but it shows it to us indirectly because the airspeed is proportional to the square root of the power output of the engine. So that's basically the instrumentation we watch, and that's what it's telling us. Now, let's think a little bit. We've said that both CHT and EGT measure power or energy that is being wasted by the engine, but let's think a little bit about how that energy is being wasted. The energy that the CHT gauge measures is energy that is being wasted during the power stroke, during the time when the combustion temperatures and pressures are at their highest, when both valves are closed, and when the cylinder is under maximum stress. And we'll see this a little bit later in another graph, but basically what CHT is telling us is how much stress the cylinder is under. It's not measuring it directly in pounds per square inch. It would be nice if we had peak pressure gauges mounted on our cylinders. They do that sometimes in test stands, but we don't have them in the airplane. But CHT is the best proxy that we have for how much stress the cylinder is under. And the energy that generates CHT, the energy that heats up the cylinder, is occurring during the power stroke. And that's the time when the cylinder and piston and connecting rod and everything are under the maximum stress, because that's when pressures and temperatures are highest. EGT, on the other hand, measures heat energy that's wasted during the exhaust stroke, because that's the only time that the EGT gauge actually sees anything. It measures the amount of energy we waste simply dumping hot combustion gases out the exhaust valve and the exhaust port after the engine has extracted as much energy from that combustion event as it can during the power stroke. So the energy that the EGT gauge measures is energy that's being generated at a time when the cylinder is under relatively low pressure and temperature, when the cylinder is in an unstressed condition, if you will. So CHT gives us an indication of stress on the cylinder. CHT gives us an indication of stress on the cylinder. EGT simply gives us a measure of inefficiency, if you will, of how much energy the engine was unable to extract from the fuel-air mixture during the power stroke, and is therefore simply being dumped out the exhaust and wasted. And as I indicated in the last slide, it's an awful lot of energy is wasted that way. We waste more energy out the exhaust than we extract and pass to the crankshaft. Therefore, limiting CHT is essential in order to eliminate stress on the cylinder and to ensure that the cylinder, has a long useful life and doesn't wind up requiring cylinder work on a frequent basis. By limiting CHT, we're limiting stress on the power assembly. On the other hand, limiting EGT accomplishes nothing particularly useful, because high EGT does not mean that the engine is under stress. In fact, most of the time, it means the opposite. Most of the things that cause EGT to be elevated are things that actually cause the engine to produce less power and to and to be under less stress. For example, one thing that causes EGT to go up would be a spark plug not firing. We see this every time we do a run-up, that when you shut off a mag, the EGT jumps up 7,500 degrees. Is it jumping up because the engine's under more stress? No, it's under less stress. When we only have one spark plug firing, the combustion event burns much slower and produces less power. That's why we get a mag. That's why we get an RPM drop when we shut off a mag, because the engine is producing less power. But it causes EGT to rise. Similarly, if the mag timing is retarded, if it's misadjusted and the spark plug is firing too late, EGT will rise. Does that mean that the engine is under greater stress? No, it's under less stress. When we have retarded timing, CHTs go down, EGTs go up. The engine produces less power than it's supposed to. And we see that in the form of increased EGT. What does the increased EGT mean? It means the engine isn't converting. Ooh, what was all that? Oh, the engine isn't converting as much energy from the fuel into power as it's supposed to, and more of it is getting wasted out the exhaust. That's why EGT goes up. So trying to keep EGTs below some value is not only doesn't make any sense, but it's kind of counterproductive. The lower, the number we really should be looking at is CHT, because that is the closest measure we have of how much stress the engine is under. Now, the one exception to this is that in turbocharged aircraft, we often have another probe called a TIT probe, turbulent inlet temperature probe. It's exactly the same kind of probe as an EGT probe. It's just mounted in a different place. It's mounted way downstream in the exhaust system, as close as possible to the inlet of the turbocharger turbine. And if the probe is in that position, it's no longer seeing little brief pulses of exhaust gas punctuated by long periods of nothing. It's seeing a pretty steady flow of gas, and it's actually measuring a real gas temperature. And we do limit TIT typically to either 1650 or 1750 degrees Fahrenheit in order to protect the turbocharger turbine blades from over-temping and getting deformed. But trying to limit EGT, which is where the probe is right close to the exhaust port and is looking at a very pulsy gas flow, that doesn't really make any sense at all, because what the EGT probe is reporting is not a real temperature, and it's not something that it makes sense to try to limit. Let me try to dispel what I call the Flattop myth. The Flattop myth is that if that in a properly running, well-balanced engine, we want to see all of the EGTs the same. We want to see our bar graph indication have a nice flat top to it, and that we really want to minimize the differences between the different EGTs. Again, the instrument manufacturers tend to reinforce this myth by having the instruments display the differential between the highest and lowest EGT as if it really mattered. On the JPI instruments, this is called Diff, D-I-F-F, and it's one of the numbers that gets displayed on the instrument is the EGT Diff. And when I constantly hear from aircraft owners saying, how come my diff is 80 degrees and why can't I get these EGTs closer together? And the answer is that's not one of the things that we're trying to do. Trying to get these EGTs closer together is not important. And let me show you why that is. Here's a kind of a simplified a drawing of a 4-cylinder engine and the EGT curves for different cylinders. Once we go through this, I'll show you some data from a real engine that's just a little bit messier, but I'm starting off with this kind of simplified drawing. But this is a 4-cylinder engine, just to keep the diagram from not being cluttered. And you'll notice that the difference between EGTs varies depending on what the mixture is. It tends to be smallest when we're operating close to the peak EGT region, which is probably not where we want to be. And if we richen the mixture out here to a reasonable rich at peak setting, or especially if we lean it to a reasonable lean at peak setting, the difference gets much larger. And the notion that we want to minimize this thing is just totally wrong, because if we try to minimize it, we're operating right where we don't want to be. And again, I'll make that clear in a later slide. What we really care about is not this difference between the highest and lowest EGTs, which really doesn't mean anything. What we're really interested in is what's called a GAMI spread. That is, the difference in fuel flow between where the rich cylinder reaches peak EGT and where the leanest cylinder reaches peak EGT. Because in a perfectly balanced engine, all of the cylinders would reach peak EGT at exactly the same mixture. That's what we really strive for. In real engines, the mixture distribution is always imperfect, and so the cylinders never reach peak EGT at exactly the same mixture. But our objective is to get them to reach peak EGT as close to the same mixture as we can. And the difference in fuel flow between where the richest cylinder peaks and where the leanest cylinder peaks is what's called a GAMI spread. And the smaller we can make the GAMI spread, the more efficient and smoothly the engine will run, and in particular, the better it will run on the lean side of peak. So that's the number we really want to focus on, is GAMI spread, not EGT diff. And of course, the instrument doesn't display GAMI spread. The only way we can find GAMI spread is to run what's called a GAMI lean test, where we simply start with a rich mixture and gradually lean it, and note the fuel flow at which each cylinder peaks, and the difference between this fuel flow, which looks like about 14.1 gallons an hour, and this fuel flow, which looks like about 13.6 gallons an hour, is what's called a GAMI spread. And in this case, it looks like the GAMI spread is roughly a half a gallon an hour, which is pretty good. General rule of thumb is that we always want the GAMI spread to be less than a gallon an hour, and preferably less than a half a gallon an hour, for optimum efficiency and optimum lean at peak operation. The smaller the spread is, the further lean at peak we'll be able to lean this engine before it starts running unacceptably rough. So that's the GAMI spread. So it's important to remember that our goal is minimum GAMI spread, not minimum diff. Diff is not a particularly useful number. The only time diff is a useful number is that when we set up the airplane in cruise, for example, we can note what the diff is. And then if the diff suddenly increases, we know that some cylinder had a big change, and there's probably something wrong, and we need to investigate it. But other than that, diff is not a significant number, and trying to minimize it is futile. It's just not useful. Now, let me show you some real data to illustrate this again. And here's some real data off of an IO550 out of a Bonanza, and this was the mixture distribution of this engine with stock untuned fuel nozzles as it came out of the TCM factory. And if we want to take a look at the Gammy spread here, we'll notice that the leanest cylinder is number 1. It's the yellow one, and it peaks first at about 14.6 gallons an hour. And then as we continue to lean the engine, of course, one goes lean a peak, the other cylinders keep rising, and they reach peaks at various points. And this blue cylinder, which is number 6, is the last one to peak, and it peaks at about 14.6. So, excuse me, about 13.3, my mistake. So the Gammy spread here is the difference between where the first cylinder peaks and the last cylinder peaks, or the leanest cylinder and the richest cylinder, and it's about 1.3 gallons an hour. That's a very high spread. This engine would not run very well lean a peak, and and even running rich a peak, it's going to be significantly less efficient than it should be. Probably burn an extra gallon an hour or so compared with a properly tuned engine. Now we take this same engine and we put tuned injectors in it, and here are the curves. Now you can see that they're not perfect, but they're a whole lot better. In fact, now the leanest cylinders looks like 4 and 5 are in a dead heat here. And in fact 3, 4, 5, and 6 are all in dead heats. And then these two cylinders, which are 1 and 2, are running a little bit richer, but the Gammy spread is only 0.4 gallons an hour, which is quite good. It's possible that if these injectors were continued to be tweaked just a little bit, we might even be able to bring this spread down a little bit more. But again, if you look at this engine, and this is now an excellently tuned engine that will run very, very efficiently and very well on the lean side of peak, you'll still notice that there's a big spread, between the hottest EGTs and the coolest EGTs. This is the thing we were referring to as diff, and it's quite large. If you looked at this on a graphic engine monitor, you would not see a flat top. You'd see a bunch of differences, and cylinder 6 is a whole lot cooler than cylinder 5 and 4 in terms of EGT, but that doesn't matter. That's not important. What's important is that within fairly close tolerances, all of these cylinders are running at the same mixture, and they're reaching peak EGT at just about the same fuel flow, and that's what's really important. So that's what we're striving for. So if EGT is not a real number, and limiting EGT is not a rational thing to do, then what good is EGT? By the way, here's an example of an engine that has these are the EGTs, and you can see they're definitely not at all a flat top, but this engine happens to be almost perfectly balanced and is running very, very well. Anyway, what's the use of EGT if EGT is not a real number, and if limiting EGT is not something that we want to do? And the answer is that that EGT is sensational for troubleshooting. The number we want to look at in terms of operating the engine and keeping it out of the danger zone is CHT. But when something goes wrong with an engine, EGT is absolutely invaluable for figuring out what's wrong. So let me just quickly go through some items here. I won't spend very much time on this, but just to give you an idea. If a magneto is malfunctioning, it will cause EGT on all cylinders to rise. CHTs will remain normal or go down slightly, but EGTs will all rise sharply, typically 75, 100 degrees, something like that, quite a large increase. So if you see all EGTs go elevated, that is almost certainly a malfunctioning magneto. When something goes wrong with a magneto, it affects all cylinders, not just one. Anytime something like this happens, we want to consider confirming it with an in-flight mag check. But if the mag has failed completely, and you switch to that mag, clearly the engine's going to quit. No big deal, but don't just follow your instincts and turn the switch back to both, because you're likely to have a big bang, a big afterfire in the exhaust system. Because even though the engine stops producing power because you've shut off all the ignition, it's still pumping fuel through, and so there's going to be a lot of uncombusted fuel in the exhaust system, and we don't really want to set it off. So if the engine quits, just throttle back to idle, then turn the mag back on, then gradually advance the throttle, and you'll avoid the possibility of an afterfire. If only one cylinder has an elevated EGT, then that's clearly not a mag, because there's nothing a mag can do that will affect only one cylinder. It's almost certainly a problem with a spark plug not firing. It could conceivably be an ignition lead, but 98% of the time it's a spark plug. If you have a turbocharged airplane with TIT readout, if that one EGT rises, the TIT will probably rise as well. But the key thing here is that we have elevated EGT on only one cylinder. In this case, it's cylinder number 5 on the left engine, and all the other EGTs are what they were before, and so that tells you that we have a non-firing spark plug. Again, it's a good idea to confirm by doing an in-flight mag check, and when you switch to the mag that's powering the bad spark plug, the engine will start to run rough, and that EGT bar will start to fall to 0. And then when you switch back to both, it'll come back to this. But at any rate, elevated EGT on one cylinder is typically a spark plug that stopped firing, and elevated EGT on all cylinders is typically a mag that stopped working. Partially clogged fuel injector will normally cause both EGT and CHT to either go up or to go down, but they both go in the same direction. If you're rich a peak, a partially clogged fuel injector will cause EGT and CHT to rise. If you're lean a peak, it will cause EGT and CHT to fall. And obviously, if the injector is clogged enough, it might even cause that cylinder to flame out, so that EGT and CHT fall profoundly, and the engine will start to run rough. If you think that you have a clogged injector, go full rich, and then land and dump your engine monitor data and figure out what happened. If a fuel injector completely clogs, then obviously it will shut down the cylinder completely, and it will cause one EGT to go completely cold, the associated CHT to drop profoundly, and you can try to unclog the injector by going to full rich mixture and momentarily activating the high boost pump. And if whatever's clogging the injector is fuel soluble, sometimes that will unclog the injector. But if the engine continues to run rough, then just land as soon as practical. The engine will be shaking pretty bad because it's running on N-1 cylinders. So anyway, that gives you an idea of how we use EGT in troubleshooting, and I'll go into more of that when we do a webinar on engine monitor data analysis. At any rate, it's very important to limit CHT. That's the key to getting long life out of your cylinders, because CHT is the best proxy we have for peak pressure. And since we don't have a peak pressure gauge, the best thing we can do to keep peak pressure under control is to keep CHTs under control. Limiting EGT is not particularly helpful or logical. EGT is not a measure of engine stress. and it often increases when stress decreases. EGT primary use is for troubleshooting. Let me talk a little bit about the benefits of limiting CHT. One thing that's important to understand has to do with just the physical structure of our cylinder heads. The cylinder heads are made of aluminum alloy, and their strength drops fairly significantly as temperature rises. And when temperature rises to 400 degrees Fahrenheit, which is right here, the cylinder head has lost about half of its tensile strength. And as temperature increases above 400, the tensile strength continues to drop quite rapidly. So TCM sets its CHT red line at 460 degrees Fahrenheit. Lycoming normally sets it at 500 degrees Fahrenheit. I'd like to try to convince you that both of those temperatures are absurdly high, and we never, ever, ever want to let CHT get anywhere remotely close to those manufacturers' red line numbers. Those numbers should be considered absolute emergency numbers. We really want to keep our cylinder head temperatures below 400 degrees Fahrenheit, and preferably lower than that. Here's kind of how I think about it. I set my kind of personal red line at 400 degrees Fahrenheit, and I have sort of a mental yellow arc between 380 and 400, and I really would like to try to keep my cylinder head temperatures at 380 or less. So if CHT starts getting above 380, I normally do something to start bringing it down. And if CHT gets up to 400, I do something fairly aggressive to bring it down, because I'm not going to let it get above 400. Here's a graph that sort of illustrates what I was saying about CHT as a proxy. The shape of the peak pressure curve and the shape of the CHT curve, both as a function of fuel flow, are roughly the same, and they peak at about the same place. Both of them peak at a mixture of roughly 40 degrees for each peak. And so that's the mixture at which our power assemblies are being stressed the most. And so it's probably, except when we're running quite low power, it's the area that we want to stay away from. And we can stay away from it either on the rich side or on the lean side, but we typically want to stay away from it. If I superimpose our little red zone that we're trying to keep cylinder head temperature down below 400 degrees, you can see that we can get out of the red zone by richening the mixture and getting out of the red zone over here someplace, or by leaning the mixture and getting out here. But you can also see that it only takes a little bit of leaning to get out of the red zone. But it takes an awful lot of richening to get out of the red zone. And the reason is because the slope of this curve is much more shallow on the rich side than it is on the lean side. So it only takes a much smaller change in mixture on the lean side to bring down our CHTs and to bring down the peak pressure than it does on the rich side. So we basically have a couple of choices here. One is that we can stay out of the high stress areas by avoiding these mixtures. This area is what the gamma guys typically refer to as the red box. And if we stay out of that area when we're leaning our engines, and we either are sufficiently lean a peak or sufficiently rich a peak, then we stay out of the danger zone. And again, we have to be pretty darn rich to do it, but we only have to be a little bit lean to do it. The other thing, of course, we can do is simply reduce power. And if we reduce power, we just slide both of those curves down. And if we reduce power enough, so that if, let's say we're at below 65% power, then typically we can put the mixture control anywhere and not produce harmful temperatures and harmful pressures. So we can either run at reduced power and sacrifice a fair amount of airspeed, or we can manage the mixture correctly, either by operating lean a peak or by operating quite rich a peak. Again, let me quantify that just a little bit. Here's a diagram out of the TCM operator's manual for the IO550 engine. There's nothing special about IO550s. The curves for any engine will look essentially the same as this, at least the shapes and relationships will be the same. And so let's take a look at this. Note the vertical dotted line is peak EGT. Note that the peak CHT and the peak cylinder pressure occurs about 40 rich a peak, as we said. If we operated at that peak point, 40 rich a peak, which is like the worst possible mixture to operate at in terms of engine stress, this engine would be putting out 83% power. This chart was for 25 inches of manifold pressure and 2,500 RPM on this IO550 engine, not normally aspirated IO550 engine. So we'd be putting out 83% power, but our cylinder head temperature would be about 425 degrees, which is not an acceptable temperature as far as I'm concerned. It's certainly below the red line of 460, but if you run your engine anywhere around these sorts of temperatures, you're going to be doing a lot of cylinder work. The cylinders are not going to be very happy with you. So let's superimpose our little EGT scale, and let's say we want to do something to bring cylinder head temperatures down to 400 degrees. So we have two choices. We can either lean to this point, or we can enrich and way out to this point. So let's take a look here. So if we decide to bring down cylinder head temperature by going lean a peak, then it's going to take about 10 degrees lean a peak to bring the temperature down to 400 degrees. If we want to bring it down on the rich side of peak, it's going to take 160 degrees rich a peak to do the same thing. Either way we go, whether we bring it down to 400 degrees at 10 degrees lean a peak or at 160 degrees rich a peak, the horsepower will drop about 4%, from 83% power to 80% power, which I think is about a 4% reduction. The effect on airspeed of doing that goes with the square root of horsepower, so it would be approximately a 2% reduction in airspeed. In a 160 knot airplane, it would be about 3 knots that you'd lose, and that would be the trade-off for getting much better cylinder longevity. Now, if it were my airplane, I still wouldn't be content with 400 degrees. I would want to bring it down to 380. And so if we do that, we now have to lean to 35 lean a peak to bring it down to 380, or we'd have to rich in some god-awful amount that's right off the scale here somewhere. And if we do that, the horsepower now drops further to 77%, and so we're going to lose another 3 knots or so. Assuming a 160 knot airplane, we'd lose another 3 knots. So that's the trade-off we have to make. To treat these cylinders right, we may have to sacrifice a little bit of airspeed. That's totally a trade-off that's up to you as an aircraft owner. And if you want to go as fast as you possibly can, and you're willing to do some cylinder work along the way, well, that's fine. I happen to be a nut on engine longevity, and from my standpoint, sacrificing a few knots to get a long-lasting engine is a good trade-off. So that's the way I operate. Now, CHT is an imperfect proxy because although the shape of the curve is the same as the shape of the peak pressure curve, it also is affected by some other things. It's affected by outside air temperature, of course. If it's a hot day, then CHTs are going to be higher than they would otherwise at the same amount of engine stress. And when I say a hot day, I'm talking about above standard atmosphere. So if you're at 17,000 feet and the outside air temperature is freezing, that's a hot day because standard temperature at 17,000 feet is I don't know, I forget the exact amount, but it's a whole lot lower than freezing. So so I'm talking if we're significantly above standard temperature, then CHT is going to be higher. If it's a very cold day, CHT is going to be lower, and we need to adjust our red line and our green arc, if you will, accordingly. Obviously, CHT is also affected by airspeed. If we're in a steep climb and the airspeed is low, we aren't getting very much cooling air over the cylinders. Obviously, CHT is going to go higher. It's affected by altitude because when we fly up at high altitudes, the air is very thin. There aren't a lot of air molecules. Basically, that's kind of the same as airspeed, because at high altitudes we're seeing much lower indicated airspeeds to get the same true airspeed, and the cooling is pretty much a function of indicated airspeed. And it also is affected by cooling system efficiency, both design efficiency. For example, the cooling system in my Cessna 310 or in a Bonanza is much less efficient than the cooling system in a Cirrus SR22 or a Diamond DA40, and so under other things being equal, the Cirrus is probably going to run 20-degree cooler CHTs than my 310, just because of it's a more efficient cooling system. Also, of course, the condition of the cooling system makes a big difference. If we have baffles out of place or baffle seals that are not in very good shape, we're going to have higher CHTs simply because our cooling system is not in a state of good repair. And these are all things that affect CHT in addition to the stress on the engine. So we have to take those things into account. Cooling system, just to make sure everybody knows how cooling systems on these airplanes work. Almost all of our airplanes are cooled this way. The way the cooling system works is that we allow ram air to enter the cowling on the top side of the engine, creating a high pressure area. We allow air to exhaust out the bottom, either through an opening in the cowling, a fixed opening in the cowling, or adjustable opening cowl flaps, to create a low pressure area below the engine. And the idea is that we want the high pressure air on top of the engine to flow down through the cooling fins on the cylinders into the low pressure air in the bottom of the engine and carry heat away with it. So to make that work, we have to have a series of metal baffles and flexible rubber-like baffle seals that together create a barrier between the upper high pressure compartment and the lower low pressure compartment, so that when the air flows from the high to the low, it has to do so by going through the cooling fins and can't just bypass the cylinders and take a path that doesn't cool them. And in addition to those baffles, we have to have a series of what are called intercylinder baffles, little plates that sit below and between the adjacent pair of cylinders and so on, so that the air can't just come down between the cylinders. It has to actually wrap around and go through the cooling fins, because if it was allowed to simply go down vertically between the gaps between the cylinders, it wouldn't be performing a cooling function. So the efficiency of our cooling system is pivotally connected with the proper positioning and fit of all of these baffles, so that all of the air that passes from the high pressure area on top to the low pressure area on the bottom has to actually go through the cylinder cooling fins and cool the cylinders, and that's the path of the air that the baffles are intended to create. So anything that's wrong with the baffles or the baffle seals, the baffle seals are the flexible stuff, and the baffles are the rigid metal stuff. But anything that's wrong with any of those things are going to cause significant cooling losses and cause our cylinder head temperatures to run hotter than we want them to. Which brings up the point that every airplane, every piston airplane, needs to have a multi-probe engine analyzer of some sort. You have to have a CHT probe on every cylinder. Otherwise, you don't know what these CHTs are, and they're very, very critical. The standard factory instrumentation that until recently used to come with most of our airplanes only measured the CHT on one cylinder. There was no guarantee that CHT was the hottest one, and you had one chance out of 4 or one chance out of 6 of catching a cylinder problem, because you were only looking at one cylinder, not all of them. So anybody that flies a piston aircraft without a probe per cylinder engine monitor is groping in the dark. And there seems to be some misconception that these things are really only necessary in high performance airplanes. The fact is that they're even more important in low performance airplanes. The less cylinders you have and the less power you have, the more dependent you are that all of those cylinders are working fine. And so low performance airplanes, Cessna 182 or Cessna 172s or Piper Cubs or that sort of thing, really need this sort of instrumentation even more than high performance airplanes do. If I have a cylinder go out in my twin, I'm still going to get to wherever I'm going. But if the cylinder goes out in a Cessna 172, it's very likely that that airplane's going to wind up on a road or in a field somewhere. So the lower performance the airplane, it seems to me, the more critical it is to have good engine instrumentation. If we need to bring CHT down, there are lots of things you can do. If you have cowl flaps, obviously you want to open the cowl flaps. If you're in a climb, you probably want to put the nose down and get a little bit more airspeed, so you get more cooling air. Adjust the mixture away from that bad area around 40 rich at peak. If you're rich at peak, rich in a lot. If you're lean at peak, probably just leaning a little bit more will bring the temperatures down, because the curve is so steep on the lean side of peak. And if all else fails, throttle back. But we just don't want to sit there watching cylinder head temperatures climb without doing something about them. One reason for that is that rising cylinder head temperatures can be indicative of an abnormal combustion event that could actually damage the engine unless you arrest it. The two abnormal combustion events we normally focus on are called detonation and pre-ignition. They're often confused with one another. They're quite different, and one is more harmful than the other, and we'll take a look at that. The way a combustion event works, it's first of all, it's not an explosion. It's a smooth burning event that normally takes a fair amount of time, roughly 6 milliseconds or so each time it happens. It starts at typically 20 to 24 degrees before top dead center when the spark plugs fire, and then the combustion continues to progress as the piston gets to the top of its travel and then starts back down into the power stroke. Normally the combustion event is fully developed and reaches its peak pressure at somewhere between 15 and 20 degrees after top dead center, and then gradually starts to cool down as the piston goes down and the gas expands and cools. If we put a pressure sensor inside the cylinder, this is kind of what the pressure would look like. It starts out as the piston starts going up in the compression stroke, the pressure starts to increase. Then when the spark plug fires and the combustion event starts, it starts rising very rapidly. It continues to rise past top dead center to the peak point that's normally, in this case, around 16 degrees after top dead center, and then it starts coming back down again. And this is the peak pressure point. In this case, it's 800 psi, occurring at 16 degrees after top dead center, which is about the optimum point. Now, it's really important that this peak pressure point occur well after top dead center, when the crankshaft and connecting rod are in a position where that high pressure can be converted into useful work of rotating the crankshaft. If the peak pressure occurred, for example, right at top dead center, then there's nowhere for the piston to go. It's basically locked in position, and so all of that pressure is spent essentially trying to overpressure and overtemp the cylinder rather than to push the piston down and do useful work. And that's why the timing of all this stuff is so critical. So if the combustion event either starts too early because the ignition is timed wrong, or if it progresses too rapidly because the mixture is set wrong, then it will reach a peak too early, and the peak will be very high. And when the pressures and temperatures get high enough, the combustion event, which is supposed to be a nice smooth burning process, will start to go unstable, and there'll be little pockets of abnormally rapid combustion that will set up all sorts of shock waves inside the cylinder. The pressure will get very high. There will be localized areas of very high temperatures. And when we look at a pressure trace in a cylinder that's undergoing detonation, this is what we see. We see a high peak and all sorts of nasty-looking ringing that is making it clear that the combustion event has stopped burning smoothly and is starting to go off in little abnormal pockets like firecrackers in a sense. And that's what's known as detonation. Now, detonation is not one of these binary things. It's not a question of either being in detonation or not. Detonation comes in all flavors, from mild to heavy. Mild detonation, or even moderate detonation, is normally not enough to damage the engine, although it's certainly not optimal to have instability in the combustion event. But we get these engines into mild detonation without doing any harm. In fact, mild detonation just keeps everything real clean. But if the detonation gets heavy enough, it can start doing physical damage. It can fracture spark plug insulators, which can lead to really bad things pre-ignition. It can do damage to piston rings. It can pit the crown of the piston, and in real extreme conditions, it can start to melt things. So we really don't want heavy detonation to occur. If you keep CHTs below 400 degrees Fahrenheit, it's almost impossible for destructive detonation, heavy detonation, to occur. So by keeping close attention to CHTs and making sure they never get too hot, you will essentially eliminate the detonation risk. And if the CHT starts rising above 400, especially if it's rising rapidly, you have to take quite aggressive action to make sure that it doesn't continue to rise, because damage can occur. Here's an example of a piston that was damaged by heavy detonation. You can see a lot of pitting on the piston crown. You can see corner melting. Sorry, I don't have my little pointer on, but pitting on the piston crown, corner melting on the piston. It actually melted to the point where the top compression ring was compromised. Obviously, this caused significant damage to the engine, and probably got quite a lot of metal in the engine, so this is undoubtedly a tear-down situation. Pre-ignition is a quite different phenomenon. Pre-ignition occurs when combustion starts at some time other than when the spark plug fires. In other words, it starts at an inappropriate time. And what will cause pre-ignition is anything in the combustion chamber that starts glowing red hot and can act as a glow plug, essentially, and start the fuel-air mixture burning without benefit of the spark plug going off. For example, we talked about the fact that detonation can cause damage to spark plug insulators. If the spark plug insulator fractures, then the spark plug can start acting like a glow plug, and can cause pre-ignition. Pre-ignition is much more serious and much more damaging than detonation. It causes enormous heat and stress on the engine, because effectively the peak pressure is occurring before the piston reaches top dead center, and it's actually trying to push the crankshaft in the opposite direction of rotation. No power assembly can survive pre-ignition for more than just a few seconds. It just puts enormous stress on the components, and so it has to be avoided at all costs. Here's an example of a pre-ignition event that happened in the Cirrus SR-20. It was actually a very new airplane. The engine was hardly out of break-in. The pilot took off, applied takeoff power at this point. We're looking at CHTs here. All CHTs came up in a normal fashion up to a peak of about 360 to 370 degrees, with the exception of cylinder number 1. And cylinder number 1, the CHT started rising in an uncontrolled fashion. When it got up to 500 degrees, the engine monitor, which in this particular airplane was an Aviation system, basically pegged out. The Aviation system does not record temperatures above 500 degrees, cylinder head temperatures above 500 degrees. But we can speculate that the temperature continued to rise to a peak somewhere most likely around 600 or 650 degrees Fahrenheit, at which point the the power assembly was destroyed, which you'll see in a minute, and everything started plummeting down. And of course, at this point, that cylinder went almost cold. And the reason it went almost cold was, well, I'll show you the next slide. But at any rate, I want to impress upon you just how rapidly an event like this occurred. The pilot applied takeoff power here. About a minute and a half later, the CHT on number 1 passed 400 degrees Fahrenheit, and hopefully he got an alarm at that point, but obviously didn't do anything about it. And from the time the CHT passed 400 degrees, which is like my personal red line, to the time that the cylinder was destroyed was less than 2 minutes. This whole destruction occurred about 3.5 minutes after he applied takeoff power, and less than 2 minutes after the CHT on number 1 passed 400 degrees. Here's what happened. It holed the piston. It melted the hole in the piston, and you can see that the piston crown was clearly above its melting point, and there's all sorts of molten metal all over the place. You can imagine the state of the rest of the engine after this thing came apart. Not a pretty sight. He sent me the date on this. He said he was going to make a warranty claim because the engine, only had about 75 hours on it since new. I told him not to waste his time because TCM never gives warranty consideration for detonation or pre-ignition damage. He made the warranty claim anyway. They turned him down, just like I told him they would. But this is a highly destructive thing. This is a pre-ignition event, and this airplane is extremely well instrumented, and had the pilot recognized that a rapidly rising CHT that is rapidly rising through 400 degrees is an emergency condition. Had he pulled the power way back and come back around and land, the engine would have not sustained this damage. But despite the fact that he had very good instrumentation, he really didn't know what to do with it, and so the engine suffered a catastrophic failure. So just to summarize some of the stuff we've talked about here, relative EGT is meaningful, but absolute EGT is not meaningful, so let's not get hung up on the numbers. Limiting CHT is important, limiting EGT is not important. We don't want to be leaning to specific EGT targets like some people are taught to do. It's just not a good idea. Now, again, one of the procedures that is taught correctly is, for example, in a normally aspirated airplane, that as you climb, lean to maintain a constant EGT. That's a perfectly legitimate thing to do. That's not leaning to a target absolute EGT. That is leaning to a target relative EGT. In other words, whatever the EGT was out of 1,000 feet, we want to continue to maintain that same EGT as we climb to 10,000 feet. But that EGT that we're maintaining could easily be 1350 one day and 1425 another day. We don't want to be leaning to a particular number. Minimizing GAMI spread is what we're trying to achieve to get a well-balanced engine. Minimizing the difference between EGTs is not a particularly useful thing, and some of the world's best balanced engines have fairly wide differences between the hottest and the coldest EGT. That is not a significant number, and it's not something that we want to try to deal with. It's GAMI spread that's important. EGT's primary value is in troubleshooting. CHT is the number we should be watching to protect our engine against overstress and damage. For optimum longevity, try to keep your CHTs below 400 degrees and preferably lower than that. And if CHT rises above 400 and is rising rapidly, you may have a minute or so before the engine is toast. So react to it rapidly and don't sit scratching your head saying, I wonder why it's doing that, because you may not have very much time to react. Okay, I guess that covers it, and in terms of the formal presentation. And so at this point I will open things up to a Q&A, and let me see what I have. Oh, got lots of stuff in my mailbox here. Good. All right, let me start going through the questions. If you do have questions, please submit them via email, not in the chat window, because the chat window stuff just scrolls off too fast, and it's in tiny little type that my 66-year-old eyes cannot read very well. So anyway, let me start down through the questions. And the first one is, from Chris DiPaola. And Chris, this is not a question I'm going to be able to answer very well here on the webinar. You sent me a photograph of an engine, and you're saying that that you're seeing some blue fuel stains on one of your cylinders in reasonable proximity to the fuel injector nozzle. And you sent me a photograph, but I hope it's not a photograph of your engine, because it looks like a engine. It's an engine that's not in an airplane, and it looks like it had an accident. And there is so much stuff wrong with that engine that I certainly hope it's not yours. Okay. But if you can send me a picture of the actual stains on your actual cylinder, I'd be glad to take a look at them and see if I can help you diagnose the problem. But the picture that you sent me, which was a engine that was not mounted on an airplane, had so much wrong with it I don't even know where to start. And I presume it's not your engine, it's an engine that you were trying to illustrate where these stains were, but I'm not going to be able to give you a diagnosis looking at that picture. You're going to have to send me a picture of your actual engine, and then I'd be glad to take a look at it. Next question is from Wayne Jacobson. Says, I own a Piper Pacer with a Lycoming 0290D 125 horsepower engine. On climb out, my number 1 and number 4 cylinders want to go over 430 degrees. Not good. I've checked the baffling and it looks very good. I'm using bayonet probes on my Electronics International UBG16 engine monitor. Congratulations on having your engine monitor on your Piper Pacer. I know Lycoming says red line is 460. Actually, I think Lycoming probably says red line is 500. 460 is normally a TCM red line. On my Cessna 205 with an IO550 engine, we keep the CHTs below 400. Yeah, the red line on that engine is 460, and you keep the CHTs below 400, which is a good thing. I'm worried about my Pacer engine. Well, I would be too, Wayne. There are two reasons normally that a cylinder head temperature will be hotter than it should be. One is that there's a problem with the cooling system, and well, I take it back. 3 reasons. One is that there's a problem with the cooling system. Second is that the cylinder is running too lean a mixture, and the third is that the ignition timing is set advanced of what it should be. So I think the first thing you really need to do is check your mag timing. If the timing is advanced, it will cause CHTs to run significantly hotter than they should, and it will also cause EGTs to run cooler than normal. We want to make sure the ignition timing is exactly on spec, and if there's any error at all, it should be on the retard side. But we definitely don't want the ignition timing advanced even as much as 1 degree from what the data plate says. So the first thing I think I would do is have the ignition timing checked very, very critically and make sure that it's not advanced at all. If the ignition timing is correct, then the next thing you need to do is figure out whether your problem is that the cylinders are running too lean, or that the cylinders aren't getting enough cooling air. And the way we need to do that is to check the CHTs both at a rich mixture and a very, very lean mixture. I mean, leaned enough that the engine starts running rough. If the CHTs on those cylinders are hot with a rich mixture and they get cool with a very lean mixture, then that indicates that that we've got a mixture problem, that those cylinders are running lean. And with the very lean mixture, they're actually running lean at peak, and that's why they start getting cool instead of running hot. If the CHTs are hot, both rich and lean, then we've got a cooling air problem. And even though you say the baffles look good, there must be something wrong with them. One of the things you might want to check is to check the inner cylinder baffles, because they're hard to see and they're often forgotten. And if the inner cylinder baffles aren't placed correctly, then air can start cruising down through the slot between the cylinders and not cool the cylinders. A good way to check that is to put a real bright light down below the engine and stand up on a step stool or a ladder and look straight down on the engine from the top and see if you can see any light in the gaps between the cylinders. You shouldn't be able to see any light anywhere. If you can see light coming through, then air can get through. So that's what I would suggest. Okay, the next question is from Samir Wallawalker. What a great name. Let's see what the question is. How much of what is being said is specific to fuel injection, and how much would be general enough to extend to carbureted engines like a Continental 320 or 360? I think you mean a Lycoming 320 or 360, because I'm not aware that there is such thing as a Continental 320 or 360 that's carbureted. And basically almost everything that we've said here is equally applicable to carbureted and injected engines, since we're just dealing with basic, combustion theory. And the only thing that really isn't applicable to carbureted engines is the discussion we had about using balanced injectors to get to reduce the gammy spread. Obviously, in a carbureted engine, you don't have fuel injectors, so you can't tune them. But other than that, everything that we've talked about would be equally applicable to carbureted engines. Next question is from Dan Niehaus. How do you lean an 0470U with a single EGT and a single CHT gauge? Oh boy. Well, the first thing, Dan, is that I have to offer my disapproval of operating that engine without an engine monitor. And I would strongly urge you to consider installing an engine monitor in the aircraft. I assure you that it will pay for itself very, very quickly. However, having said all of that, in the absence of decent engine instrumentation, the way you would lean that engine is the old-fashioned way. And the old-fashioned way is that you lean the engine very slowly. Hopefully you have a vernier mixture control so you can do that. You lean the engine to the onset of roughness, and then you enrichen it just to the point that the roughness goes away. And that's about the best you're going to be able to do without proper engine instrumentation. And it's actually not a terrible procedure. It's a procedure that I use when I'm flying aircraft without proper engine instrumentation, like Super Cubs on floats and stuff that I occasionally will do. But certainly if I owned the airplane, I would run, not walk, to install proper engine instrumentation. The next question is from Tom McDermott, and Tom says, could you discuss lean of peak operations in cruise? Tom, that is a sufficiently rich subject that I don't think that it would be reasonable to try to get into it here. What I really need to do is schedule a future webinar that specifically discusses lean of peak operation. And I will do that. You have my commitment on that. But I don't think I can really get into that's such a broad question and would take so long to answer that I don't think it's reasonable to try to address it in this webinar. The next question is from James Barno, and it says, on climb out, my cylinders 1, 3, 4, and 5 get too hot, sometimes as much as 420 degrees Fahrenheit. When I level in cruise, temps come way down to 360 to 375, and 2 and 6 run cool constantly. What's up? And the airplane is a Cessna 182. Well, again, Jim, I sort of addressed that with the previous question, and my comments there really apply equally to you. The first thing I would suggest you do is check your mag timing and make sure it's spot on and it's not advanced, because that's something that will definitely drive up your CHTs. And if the ignition timing is correct, then you need to determine whether the high CHTs are due to inadequate fuel flow or whether they're due to inadequate cooling air. And the way we do that is to check the CHTs both with a very rich mixture and a very, very lean mixture. And if it's a cooling air problem, the cylinders will be hot, whether they're rich or lean. But if it's an inadequate fuel issue, then the cylinders will be hot when we're running a rich mixture, but they'll actually become cool when we're running a lean mixture, because those cylinders that are short on fuel will wind up going on the lean side of peak, and the CHT will drop off pretty rapidly. So that's the way we that's the way we diagnose it. It's basically a three-step process. And I hope that answers your question. The next question is from Jesse Kempa, and it says, regarding running a normally aspirated airplane's richer peak and engine health. Some people say in a normally aspirated airplane, anything above about 7,000 or 8,000 feet density altitude, you can put the mixture anywhere you want to. I agree. We kind of showed that on one of the slides, that when you climb up to 7,000 or 8,000 feet, the power output of that engine at full throttle is down well below 65% power, and below 65% power, you can probably set the mixture anywhere you like and not get into the area of damaging temperatures and pressures. And I think we saw that on one of the slides that I used. And then it goes on to say, the operator's manual for my Lycoming IO 360A1A states that I can make 75% up to 10,000 feet. Doesn't say what kind of airplane this is. I guess I would have to see the manual, because unless the engine is a derated engine in which you are not allowed to go to full throttle at sea level, I can't see how you can make 75% up at 10,000 feet in a normally aspirated engine. But I'd have to take a look at your operator's manual. I guess that's all I can say about that. It says, at what density altitudes can I run safely at 50 richer peak and normally an aspirated engine, assuming wide open throttle operation? Well, again, I can't give you exact numbers, but if you lean to 50 richer peak and your cylinder head temperatures are, modest, then you're fine. If you lean to 50 richer peak and your cylinder head temperatures get higher than are comfortable, then you're not fine, and you need to either operate lean to peak or operate richer than 50 richer peak to bring them down. Okay, the next question is from Ken Lane. Oh, it's a question about, can't get into the webinar, so I guess there's no point in dealing with that. Next question is from Bill Berger, and It's a question about EGT imbalance. SR22 normally aspirated IO550N platinum engine, fine wire plugs. The issue is that the number 6 cylinder has EGT 75 to 125 hotter than the rest on lean run-up. Only slightly hotter on rich run-up. EGT is significantly hotter on number 6 when running lean on the ground or at low power, but only slightly hotter when cruising rich at peak or lean at peak. Just reading the rest of it to see. The answer is, Bill, that EGTs at really low power settings, particularly on the ground type power settings, can vary all over the place because you can wind up having very turbulent flow in the exhaust system at very low power settings that can do very, very bizarre things to EGTs. And the best advice I can give you is to pretty much ignore EGTs during ground operations. An EGT spread of 75 to 125 is not anything I would be concerned about. I mean, my airplane is about as well balanced as any airplane I've ever flown, and when I'm running profoundly on the lean side of peak, I frequently have 100-degree differences or 90-degree differences between the hottest and coolest EGT. As I indicated, it's just not important. Trying to keep a flat top is not something that we really need to worry about doing. From your description, it sounds to me like this is not significant and it's not something you need to address. However, if you would like to dump your Emacs data and upload it to the cirrusreports.com website and then send me an email with your N number, I will go look on the Cirrus Reports website at your data and be glad to give you my impressions of it. But from your description here, it sounds to me like it's not something you need to worry about. Next question is from Sarah Seward. It says, I've used the application of carb heat. I think that's supposed to be a ½ inch or more. It looks like a ½ a foot, but to find out where on the EGT temperature curve. That's not a sentence. I'm not sure what that means. If temp increases, I'm on the lean side of peak. If it doesn't move, I'm at or near peak. If temperature goes down, I'm on the rich side of peak. This lets me see the relative position of each cylinder at a given mixture setting, with all cylinders having an EGT. In carbureted engines, there is always a wide disparity of fuel distribution among the cylinders, and this lets me know when I'm optimally leaned without moving the mixture control, which always has lots of slop in its travel. Any comment on this technique? And it's signed Ed, although the from says Sarah. Well, Ed or Sarah, that's certainly a novel approach. I don't have any problem with it. Applying partial carb heat has essentially the same effect as richening the mixture, and so if you use that approach to richen the mixture rather than to move your mixture control because your mixture control is not vernier and it's got too much slop in the control, that certainly seems like a valid procedure to me. I've not heard of anybody doing that before, but I don't see anything wrong with it. And as I said, applying a little bit of carb heat has exactly the same effect on the engine as richening the mixture a little bit. And so, as far as I'm concerned, what you're doing is perfectly valid. The next question from Andres Darvazi says, why the difference between EGT and TIT? generally TIT being slightly higher if it is downstream from the exhaust. Well, again, think about it, Andre. The EGT probe, which is sitting very close to the exhaust port, is seeing brief pulses of hot gas punctuated by long periods of no flow at all, during which the probe, doesn't heat and actually has a chance to cool down a little bit. The TIT probe, which is mounted way downstream in the exhaust system, where it's seeing the combined output of all of the cylinders, and most of the pulsiness of the flow has gone away by then, so it's seeing pretty constant gas flow, doesn't have any opportunity to cool down because it's seeing a constant gas flow. So you would almost always expect TIT to read higher than EGT, because the EGT probe is reading short pulses of hot gas, and the TIT probe is reading a continuous flow of hot gas. And so the TIT probe is going to reach a higher equilibrium temperature than the EGT probe will. And I hope the slides that I put up illustrated the pulsiness of what, if that's a word, of what an EGT probe sees. But that's the reason. Okay, the next question is from Dean Tabor. Lots of talk about running Lena Peak and GAMEs, which are great for injected engines. How about discussing how a carbureted engine should be run related to EGT and leaning? Well, again, getting into leaning is probably a webinar unto itself. You're flying, Dean. You're flying a Cessna 182 with an 0470 J with an 0470 U engine. So they must have retrofitted that U engine because the J came with an R engine, I guess. But in any case, the 0470 among carbureted engines has amongst the worst mixture distribution of any carbureted engine, and so it's a lot harder to run an 0470 engine Lena Peak than it would be a carbureted Lycoming, for example, an 0320 or an 0360, because the Lycoming has a highly symmetrical induction system and it has inherently better mixture distribution. Not as good as a well-tuned injected engine, certainly, but reasonably good. The 0470 is sort of notorious for having terrible mixture distribution because of the geometry of its induction system, with the carburetor mounted way in the back instead of in the center of the engine. And as a result, 0470s tend to have poor mixture distribution, with the front cylinders, 5 and 6, always running much richer, and the rear cylinders, 1 and 2, always running much leaner. On an 0470, you can improve the mixture distribution in two ways. One is to avoid the use of wide open throttle, and instead of running the throttle wide open, back it off just enough to get the slightest decrease in manifold pressure, just half a needle's width. What that does is it cocks the throttle butterfly in the carburetor and creates turbulence in the airflow as it's going through the carburetor, which improves the fuel atomization and reduces the mixture distribution problem. Makes the cylinders run closer to the same mixture. The other thing that you can do is to run a little bit of partial carb heat, particularly if outside air temperatures are cold, because again, preheating the air as it goes through the carburetor improves atomization of the fuel and reduces the spread of mixtures between the front and the rear cylinders.